This is the additive manufactured Blisk. So we've got additive manufactured from a company called BeamIT, which is part of our Sandvik Additive Manufacturing enterprise. And the idea is obviously there's less material to machine off, making it a much more productive way of machining a Blisk. So a Blisk normally comes from a solid forging or a solid piece of aluminium where it's a full piece of material which we have to then machine out every part of the material, which obviously then takes a lot longer to machine out, and there's a lot more waste material, and obviously the machining time takes a lot longer. So the actual way of doing this is a new enterprising method of doing it, which we hope the market takes to and goes forward with.
Together with Seco, then we have looked at different parts that have been printed with additive technologies. We looked at powder bed fusion laser then for producing this Blisk. And we have done it together with our strategic partner BeamIT down in Italy. They have a larger machine than we have here in Sweden, so we had to turn to them to really make the size of that Blisk that was needed. So the concept that we want to show here is that we can produce this very near net shaped fine parts with additive, but still you need that final touch with machining to get the really surface quality desired by our customers then. And here, I mean, joint forces, Seco and Sandvik Additive can really show the possibilities that you can have in future production using both additive and subtractive methods. I think any customers coming looking for a future production solution for their components can really see the benefits having both Seco and Sandvik Additive in the same family, helping them out with all the way from the powders that we are producing, that we put into the printer, knowledge about how to print them, and the waste knowledge that Seco has when it comes to machining these fine parts. So they really get a good partner in turning to us to help them out with their future production or manufacturing setup. Yeah, I mean, the first thing you do when you ideally when you get the new component or part that you should print, you redesign it so it's really designed to get the most benefits out of additive. When you have done that, or if you have your final drawing, then you need to be able to place it in the machine and to be able to control the tensions and the heat that builds up when you're melting this within the AM process. You need to have support structures going down into the build plate. And these needs then of course to be removed afterwards and machined. And also, I mean, the as-printed surface looks more like orange shell or something. It's not super smooth. So if you know that you will machine certain areas, you add a thin layer or a little bit of extra material that you then will remove to be able to get the high quality surface that you need. And we're talking parts of a millimeter here that you add. So that is something that you need to take into account really in the building phase, design phase, to put that onto your drawing before you build it. Otherwise you will end up with a component that is not in the right size after machining.
So the main thing for this particular demonstration is to prove any advances in workflows and better ways of making parts, in this case an additive manufactured Blisk. Typically, traditional processes for producing a Blisk would be machining it completely from solid. So that takes quite a long time. It wastes a lot of material because you're obviously losing metal. So Seco's innovative idea is to additively manufacture the Blisk in the first place.
So the additive manufacture comes from the 3D printing of the Blisk. So they try to get this Blisk as near to net shape as possible, because traditionally the Blisks are just manufactured or machined out of a large billet, which causes a lot of time and a lot of money because of the material wasted. So the measuring device that we've got behind us is the Atos scan box. So the Atos scan box is an off-the-shelf automated system from GOM, and the scanning head that we've got, or the sensor, is the Atos 5 airfoil. So this is a relatively new system that measures very small intricate parts on a small measuring volume. Okay, so ordinarily with a CMM system, the CMM will go and measure on the parts that have been specified by the technical drawing or other. Whereas with our system, we're able to capture full field data.
Full field data allows us to capture surface geometry all the way over the surface of the part. So even if the part's gone, we still have all that rich data, high resolution data at our fingertips to be able to inspect against later.
So the sensor can be maneuvered to actually look and gather information from the supports. So what would happen after this process, so after it's been additively manufactured, would be a machining process. So the machining process will need to take into consideration where those supports are. So our data can help alleviate problems with tooling collisions and others, and it can actually already give the information as to where those supports are, so that the cutting tool can concentrate on removing those supports and then manufacture the bliskers to specification after that. So the first process that we go through is the photogrammetry. So the photogrammetry gives the relationship between all of the reference points. So the second process is the scanning. So this will use the reference points to know where we are in 3D space, and then it will project a fringe pattern onto the part, which then gets tracked by the two cameras, and then this is what gives us the scan image. So then we'll scan the part, and then this will get fed through to our computer, and then at the end, after the series of scans, we're able to then pull all this scan data together, fit the scans, and then we're able to polygonize, which is turning that 3D point cloud into a mesh that we can extract dimensional information from.
Again, so the next stages of the process are typically CAD/CAM programming, machining. So a lot of those processes rely on having good quality data so that they can make sure the cutting tool paths are correct, the machining is correct so that they don't take off too much material, etc. And the full field data from the Atos system allows the next stage processes, so machine cutting paths, it allows those to be optimized so that we only take off the material we need. Cycle times can be reduced because we don't take any cuts that aren't necessary, for example.
A Blisk machined, so we're doing the machining on a Blisk that's being created by an additive process. So this is quite a challenge, as there's lots of little bits and pieces from the additive process that is part of the Blisk design. And we are going to turn and mill this Blisk. The big issue is time. So we're going the first point is to radically reduce the machining time that's associated with Blisk machining. So that usually is a very long process that you go through. I think one of the second points is obviously this is a high-end component, so this is a very specialized product, and usually it needs specialized people to machine it. So what we're going to show is how fast and simple you can machine and create tool paths on something as complex as this Blisk project. And I think maybe the third topic is really in these times we're all doing it virtually. We have to present a project and demonstration which is being done remotely. So we're using our tool called Virtual Machine to show how easy it is to transfer data in the virtual world, the CAM world, onto the machine to give an enhanced experience for the operator and give him trust that what we're doing is right first time. The thing is the turning. You start with the turning, so let's start there. The B-axis simultaneous turning. This is a nice enhancement in our portfolio. Here we're using these parts are complex, so getting into these difficult to reach areas is an interesting challenge. So complex geometries need a solution that's not complex but simple to use. Otherwise, if it's not simple, you won't use it. So here we're using a simultaneous machine. The trunnion of the machine tool is actually moving during a turning operation. This is called B-axis simultaneous machining, and this allows us to get these tools into the more complex, difficult areas. Because we are also using or cutting these areas and finishing them with one tool, this allows us to remove all the blending problems you would get using multiple tools in different angle orientations to get into these complex areas. And because we're cutting it with one tool, obviously you then reduce the tool count, so the number of tools is dramatically reduced as well.
This is quite a new, innovative situation in the market. So we're cutting it with Seco. The idea is that the machine lends itself to cutting a Blisk very accurately, and the big thing about the Blisk is the rigidity of the machine. So the spindle is a horizontal spindle which is actually supported very, very near the actual cutting tip. So that gives you the rigidity that you need for cutting titanium and titanium blades. If you've got rigidity, that actually means that you get better tool life and you get better accuracy as well. On this machine that we have with Seco, this particular machine has a high accuracy package on it as well. So that's giving you the extra cooling on the machine. It gives you extra protection against air intake, which actually can cool the machine down and causing a vortex. So we actually put a system around the machine that stops that intake of cold air and cooling down. So we're keeping a very constant temperature on the machine, and the ambient temperature around the part and the machine.
We think that coolant's very important for all materials, but particularly with your exotics materials. There's a huge amount of development work goes on with people like Seco regarding the geometries of the cutting tools to mean that you can achieve good production rates, good surface finishes, etc. If you use a poor quality cutting fluid, you might not optimize your performance. So from our point of view, we think that the better quality of the cutting fluid will mean your production costs can come down, but more importantly, with these materials, if you have excessive tool wear or even worse, breakages, that can create work hardened surfaces, which can turn an already awkward application into an almost impossible application. What you want is high lubrication when you're doing your machining, because obviously we want to try and reduce the heat that we generate whilst we're machining. So you want high lubrication, but you don't want to run too high on the concentration of the coolant, because that detracts from the cooling process. So if you go for a rapeseed ester product, it gives you the very high lubrication, but you can run it at sort of 8-9% is perfect for it. So it gives us the best of both worlds. We can still create the cooling process and give you high lubrication, which should mean that you should get better tool life from your roughing tools. And when you come to your finishing processes, you should get better surface finish, and you should get longer tool life before you start to see wear on those finishing cutters, which, as we said earlier, regarding the work hardening complications that you could get, can help on that front.
So you've got that rigidity, but you've also got the flexibility on the table. The table is only supported on one side, unlike a trunnion that is supported on both sides. It gives you much more versatility and accessibility to the part, and for blades that's a really good benefit.
Companies like GROB came up with this amazing solution of mill turn machines. Technically, fantastic solution, gives you a lot of flexibility, but it has a few caveats. For the table to be able to do all of that, it does impose you a limitation on the weight of the workload. That's when Schunk came up with this quite unique concept of the rotor flex system. So the rotor flex, basically what you're doing, you're using a very small chuck that will cover a massive area. So in this particular case, we're using a chuck, if I'm not mistaken, is about 300 mil, but it will cover 750 millimeters of turning diameter. What does that mean? You have an incredibly solid work holding with an incredibly flexible approach to it that can be made to work parts from 50 mil to 750 mil without changing of the work hold and without overloading the machine. So you make the most of the flexibility that the machine is offering you. This application that we're running here today is an extremely demanding application. Blisk cutting brings a lot of vibration to the equation, and the tolerances are extremely tight. By working with the rotor flex, the level of effort into adjusting the work holding to the solution is minimal. We just needed to come up with some special jaws, soft cut jaws, and that was it. So with, like I said, the flexibility is the name of the game here, without compromising any of the rigidity and the strength. So with a work holding, that you could start from 50 mil going to 750 mil with minimum effort, you can deliver a solution as demanding as this one. And now talking about Schunk as a whole, this solution, amazing, and will do most of the things that you need. If there's a demand, if the complexity goes a little bit over, then we could step in and try to find you special solutions. We now have a whole group inside the company just working for aerospace and finding solutions specifically for the industry. Like the design of Blisks and long span. We have, I don't know if you're going to be seeing this on a video, but if you do, there's a very long part behind me that was made on a Schunk work holding that is designed for long aluminum ribs that build up a lot of tension, and the work holding itself is designed is a 0-point system that will allow tensions to be released and be locked in again. Not necessarily a conversation for today, but this is just a taste of the things that Schunk can do when it comes to highly demanding work holding solutions.
One of the things about the GROB machine is very different to any other machine on the market. It's a unique machine. So it actually gives a lot of things that people don't really understand, and you know, people need to come and talk to us to be able to understand this, because you can see it, but actually when people stand in front of the machine, very often they go, wow, we didn't realise it could do that. So although it's good on video, it's never as good as actually standing in front of the machine. We have this machine here with Seco, and and other partners. I mean, we've got some really nice work holding on there from Schunk. You know, the work holding can make a difference as well to your part. What you're holding, that needs to be very rigid and good. That's a quality piece of kit that we've got holding the part. And then you can do lots of different things with these machines that people don't realise. The machine has been around for a long time, but it hasn't been in the general market because we've always been in automotive. But what we've learned from automotive, we've now transferred into this machine, which is a universal machine. And it can be anything from a medical part to an engine, which they're known for, GROB are known for, to make engines. And we do the long crank boring, so that's where the longest part, but the longest tool with the biggest part comes into it. But you can do mould and die. We sell these to many people, but with this machine here at Seco, we can actually take somebody's part and we can cut it and they can come and see it, and we can do that very quickly. Actual fact, we have actually, during this period of COVID, we have actually taken an inquiry that we could enabled us to cut the part here for the customer and deliver the machine all within the COVID period of time. So by having this machine here and the tools and the expertise from Seco, as in cutting tool people, and our collaboration with knowledge on the machine, open mind programming it, and being able to hold it with some very good work holding, we've been able to supply that machine to the customer.
Obviously the collaborative side of this thing, us working with Open Mind and Schunk and GROB, and even Jemtech, the coolant supplying partner. By working together on these components, we're able to give massive productivity gains, which also affect the environmental impact of the actual part, because we're not having so much scrap material. We're looking for in excess of 50% productivity gains from the machining cycle time, and obviously looking at the amount of material that we're not going to be wasting, there's a huge amount there as well, potentially again up to another 50%. All this leads into greater tool life, because the tools don't have to take so much material away. You don't need so many more tools to actually produce these parts, so therefore the tooling costs come down. So from a cost and a productivity, it's a gain all the way.